to IIRS for giving me this opportunity. So very good evening, all the participants. Today we shall be talking about deep learning, which has come out as a very important research tool for finding solutions to difficult problems. Here we shall be talking about deep learning models for classification, object detection, and segmentation. Let's talk about intelligence before we go ahead with this, because deep learning has evolved as a wonderful representation learning mechanism which has boosted the performance of AI systems. So when we talk about AI systems, we should know what we mean by intelligence. So intelligence means ability to learn, understand, and think in a logical way about things, which is what is dictionary meaning. Or we can say that we make judgment or have opinions that are based on reasons. That is what is intelligence. So when we talk about artificial intelligence, what is AI? Now, AI can be anything that deals with systems that think and act like humans, systems that have a rational behavior, or attributes that systems that have attributes like emotions, reactions to given situation, many things, right? So these are examples of AI systems or AI-enabled systems. You must have heard about Sophia, the world's first robot to get a citizenship. Or during the COVID time, I've seen many experiments. You must have heard about many experiments dealing with patients through robots, where these robots are intelligent. Or think of autonomous cars like Tesla. Or think about your phone. In your phone, we have Siri or Google Assistant, or we have systems like Alexa. These are all examples of intelligent systems. So AI is a constellation of many different technologies working together to enable machines to sense, remember that sense, comprehend, act, and learn, which is very important, with human-like level of intelligence. We keep learning, right? So maybe that's why it says that it seems as though everyone's definition of AI is different. So AI is not just one thing. So whenever we talk about AI, it is human intelligence that we are looking forward to, right? To mimic the human intelligence. So if we look at the evolution of intelligence, artificial intelligence, it is basically, there has been a lot of booms and falls in the history of AI. But in the recent time, it is deep learning that has brought the AI into the forefront again. So what is deep learning then? Deep learning is a special kind of AI models that are basically type of machine learning models, and machine learning models, specific models that have representation learning mechanism. So deep learning is basically a new representation learning paradigm that automatically learns features or patterns from the given data and makes decisions or predictions. That is what is deep learning in short. Because we have seen several examples of machine learning in the past couple of days, so you must have seen that we start with the input, whether it is in satellite image or any other image or any other data. We start with an input. We make use of feature extraction algorithm, which is a manual feature extraction we call. Then we send it to classifier. The classifier classifies it, and then maybe if it is a classification of the image to be having car or no car, then it will give you the output accordingly. In contrast to this, my dear friends, deep learning does the feature extraction and classification all in one stage. So it learns the features automatically. You need not worry about which feature should be the best possible 100 features or what could be the best method of extracting features. You have to simply give the data, and that data is fed to the deep learning models, and it automatically extracts features and classifies it, right? So that is the basic difference, that it is able to automatically extract features. Why? Because it learns. The idea is how we learn the representation of the data. So while it is learning the representation of the data, it is extracting features for different types of entities in the data. So deep learning, it basically learns rich hierarchical representations, which are features in hierarchy, automatically by extracting features at different levels. And it also provides a flexible, learnable framework. That's important. Flexible in the sense that you train it in a different environment for a different data set, and then you try to refine your results on a different data sets. So it gives you a flexible, learnable framework. Trained algorithms work for a broad range of problems. What does that mean? Well, it's not as broad as you can expect from humans. Humans have, if you tell them the examples of a tree, for example, so by looking at 2-3 examples of trees, a child learns quickly that this is what is a tree, this is what is a shrub, this is what is a small plant, and this is what is a sapling, right? The same kind of intelligence we expect from deep learning models. So to a broad range of problems, deep learning models are able to give you the solutions. That is the best part of it. So take this example, for example, suppose the problem is image caption generation. So here there is a bird which is hiding in a bunch of flowers. So what this deep learning algorithm will do, it will first extract low-level features like color, edges, and then will combine those features to make some elementary level, mid-level features like circular objects or some curved objects. And then it will further combine those to create high-level features. And then these features will go to certain last layers of deep learning models, where it will be classifying them or will do whatever task is assigned to the deep learning model. Not always classification. It can be object detection. It can be segmentation as well. So because of this deep learning, there has been huge development in practically all fields. Take the case of internet or cloud. So image classification, speech recognition, language translation, which was very difficult some 7-8 years ago, but now language translation is much improved using the deep learning models. In medicine and biology, drug delivery, drug discovery, all these methods are showing much improvement. So take the case of autonomous machines like robots which are moving autonomously, vehicles. So think of any field, you will find that deep learning is there. So the other day I was thinking of buying a camera from Canon, so I thought to explore the website of Canon cameras, and there was one camera that says that deep learning enabled image stabilization and other systems. So you can see that everywhere deep learning is there. So what are the ingredients of deep learning? Basically, the deep learning models use artificial neural networks as the learning machine or learning algorithms which are applied are on these artificial neural networks. Data, algorithms which are important. How do we train? The machine will be the same, but how do you train the machine so that it learns better, it is able to recognize this in a faster way? So algorithms to train ANNs, and then computing resources. So we have 4 ingredients, and therefore artificial neural networks, you must have heard by now, you must be very much familiar with what are artificial neural networks. They are basically an effort to produce a replica of human brain where we have layers of neurons. They interact, each layer interacts with the next layer, processes the information starting from the receptive field, which is eye, ear, nose, skin. These are sensors. From here, these informations are processed, and then it is sent to the next layer. Next layer further processes, sends to next layer, and so on and so forth. And finally, the action is taken. That is, the decision is made, right? So this is what is artificial neural network. So there are various types of neural networks. Multi-layer perceptron, you must have heard, convolutional neural networks, recurrent neural networks, and there are variants of these types of neural networks. Lately, there is another type of network that has become very, very prominent, and that is known as a transformer. Transformer. These are very important networks that are coming. So when we talk about convolutional neural network, you know that in the multi-layer perceptron, every neuron here is sending information to all the neurons in the next layer. But the question is, do we need actually these edges, all these information to be propagated to every single neuron in the next layer? Is it really required? Can some of the weights be shared? Like, you know that when this neuron is receiving, when this neuron is receiving information, it assigns different weights to different inputs. The same way, like you will be giving higher weightage to maybe the input given by your reliable source friend than the input given by any other friend. So it is the same thing, that I give higher weightage to, for example, while choosing clothes, I will be giving higher weightage to, say, green colors, because I have liking for green colors. And you may give lower weightage to green color. So every neuron will give a weightage to the input received from the previous layers, right? So the question is, can the weights which are used by this neuron, can this neuron also share the same weights, and try to learn maybe something similar, or using these weights? That is the question. So image understanding, if we look at the image understanding, patterns to learn can be very small compared to the image size. So for example, let's take this car detection in images. Car is very small, image is huge. But so a small pattern detector can be used in place of the entire weight parameter matrix, right? So that was the reason we thought that we will be making use of filters that will be sliding on the whole of the CNN, and then that CNN will be picking up the patterns, right? Will be learning the patterns. Sorry, that CNN will be learning the patterns through the filters. Those filters will be actually learned, right? And see, the same pattern can be at different positions, right? So the same pattern detector can move around and detect, say, it's not eyes, airplanes at different positions. Sorry, this is not eyes, airplanes. the different positions, right? So how do we do convolution operation? Convolution operation is very simple. Think of a filter, just put it over a image, and then whatever are the entries, take the dot product. So convolution with the image block outputs a real number. By taking the dot product of the entries here, with the entries in this filter, right? When we slide this filter over the entire image, block by block, we get an array of real numbers. So this is one real number. When you slide it here, you will be getting another real number, right? That is the output of the convolution operation. So you have, suppose you have slided this over the entire image, you will be getting these, this is the output image, right? So this is how we get the output of a convolution layer. And for each filter, see why we are choosing several filters, but why? Because from the same image, we would like to learn different things. From the same image, we would like to learn different things, right? So let's take this example. Let this be the image here, right? And this be the filter, right? So let me first take the dot product of this image with this filter. So I convert the image block and filter into a single column vector. So what I do is, let me check this. Let's think of this as a single column vector, 517, 725, 535. So this becomes a single column vector. And then we also have a single column vector here, right? You take the dot products. So how do we do? W transpose X. Because if I have to multiply this with this, so you will have to take the transpose, right? So W transpose X becomes 2. When I take the dot product of this, I get 2. That 2 is the output of this convolution operation on this part of the image. Similarly, we will be taking it here. I will be getting another number, right? You get -7 in this case. In this way, you will be getting the output from this image. So what will be the output size after the convolution? It will be, you can see that this is one output, the second output, the third output, and the fourth output. So it will be 4. Then I will be sliding it down here also, so it will be 4 cross 4, right? Now, if it is an RGB image, then there will be several channels, 3 channels, and on each channel you will be applying this convolution operation. And then you will be getting 3 outputs, right? And these 3 outputs, how do we do? You will be first of all, we make 3 copies of the same filter and apply convolution operation on the R channel, G channel, and B channel. So you will be getting 3 outputs, 1 output from R, 1 output from G, and 1 output from B channel. You will be actually adding those to get the combined output. So from one filter, whatever number of channels are there in a multispectral or hyperspectral image, there can be many number of channels, right? And on each channel, you will be applying filter. And suppose there are 14 channels, then you will be applying filter on all 14 channels. You will be getting 14 arrays of numbers. You will be adding all those 14 arrays and you will get one single array, right? By the 2-dimensional array you will be getting. And that will be the output of the convolution operation for one filter. So if there are several filters, if there are H filters, which will be learning different things in the convolution, in the image, filter 1 will be having a task of learning, say, eyes in a face detection system. Filter 2 will be having the task of learning nose. filter 3 lips, and so on and so forth. So every filter will be learning something different. And some of them will be learning the same thing as well. So size of the output will be, in case if it is a 6x6 image and 3x3 filter, then size of the output will be, for one filter it will be 4x4, and if there are H filters it will be 4x4x H. So you can see that input size of input images of size n cross n, and if there are H filters, each of size f cross f, then output will be having H feature maps. These are known as feature maps. They come out as the output volume from a convolution operation. I hope this all has already been covered, so I'm going fast. So activation map will be generated. How? From those feature maps, we will be applying on each entry. Suppose you have got a feature map and there are certain entries, suppose 7, 2, 9, 3.5. On each of these entries, I will be applying an activation function. The same thing, same as we did in case of multi-layer perceptron, to introduce the non-linearity. To better represent a non-linear data, these activation functions are applied. So on each entry, we will be applying activation function, and so we will be getting the activation maps. So if there are H filters, you will be getting H feature maps. From those feature maps, on each of these entries of those feature maps, you will be applying activation function, and you will be getting activation maps. Sometimes in the literature, you will find that activation maps and feature maps are considered, are used interchangeably, right? So we stack these up to get a new image of size 28x28x6 in case when you have a 5x5 convolution applied on this 32x32x3 image. So this is the activation maps that we have plotted from this input image. Suppose the input image is this leaf. You can see the activation maps from coming from the second convolution layer, the fourth, the seventh, the 10th, and this. So you can see the level of abstraction goes with the number of convolution layers. So these are more abstract type of features that you will be getting at the deeper the convolution layer is, right? So these are the activation maps, the output obtained after convolution operation, and then on the convolution operation you are applying activation function. So you can see that they are learning feature maps. You can see that this and this are almost learning same thing, right? Maybe this and this, they are learning same thing. So there are redundancies in the learning, feature learning. Why redundancy? Why, how many filters should we take? There's no, hard and fast rule for taking number of features, but we take a sizable number of filters so that there is nothing lost while these features are being learned. There can be redundancy. So if one filter is not able to learn properly, the other filter will supplement it, right? So that is the reason we take large number of filters generally. If there is a lot of detail in the image, like in satellite images, there can be many details. You must take large number of filters. So what could be suppose you have applied a convolution operation, we call it a convolution layer. What is the input size and what is the output size? If suppose the image is of size n cross n, you have a filter of size f cross f, then the output size turns out to be n minus f plus 1. What is the stride here? If we shift by only 1 pixel, we call stride is 1. If we shift by 2 pixels in some images, large images like 7,000 cross 7,000 images, you may have to further take the grid of those images and process those 7,000 cross 7,000 images into pieces. And then on each piece, you can have a stride of 2, 3, 4, just to be more computationally efficient. All right. There's something called zero padding. There are 2 advantages of zero padding. And one advantage is like this, what happens that if you have a corner pixel, see in satellite images, sometimes the corner pixel can be a very important pixel, right? But if you see the convolution operation, what do? We first apply here, and then we apply here, then we apply here. So if it is an interior pixel, it has greater say or greater role in decision making or feature learning. But this corner pixel is only appearing once, right? So corner pixels have better contribution if we apply zero padding. That means I'm enhancing the size of the image by adding the pad 0 here, right? That is known as zero padding. And if I apply, say, convolution operation, you just saw that a 6x6 image was converted to a 4x4 image. So dimension reduction is done. That can be controlled. Because why you need dimension reduction? So suppose you have a 7,000 x 7,000 image. You have taken the grid, and each image, each sub image, suppose this is 7,000 x 7,000, right? And you've taken the grid of this, and each cell of this grid is fed to the convolutional neural network, right? Now, here, the corner pixel here was, just look at it. This corner pixel must be having some other part here. So this must be important. So when we are taking grids, this grid can turn out to be, say, 512 x 512 grid. And this 512 x 512 may have corner pixels or edge pixels that are important. So on one hand, you would want that dimension should not be drastically reduced by when you go deeper with the convolution operation, because this next time when you will apply, this will become 2 x 2. So that will be reducing the dimension. So just to reduce the, to slow down the process of dimension reduction, we do that. There's another thing which is known as pooling layer. Pooling layer basically is a subsampling layer, where what we do, after the convolution operation, you apply some kind of subsampling, and I will tell you what kind of subsampling we generally apply. So the image characteristics remains the same. Only thing is that to deal with the, because your convolution operation or the convolutional neural network requires huge computation. Therefore, we downsize the size of the image, right? So max pooling, for example, what is pooling? Suppose this is the image, which is coming as a feature map from the, yes, I'll take the maximum of this. Say, suppose the maximum is this. Here the maximum is 0. Here the maximum is 5. And here the maximum is 4, right? So, fine. So I'll take 7, 5, 0, and 4. So this 4 x 4 becomes 2 x 2. Similarly, here, for each filter, right? So max pooling basically downsizes the image. Similarly, there is average pooling. So here we take the average of this. So 3 plus 2 plus 7, 13, so it is 13 by 4. So 13 by 4 is 3, right? 13 by 4 is 3. Similarly here, here, here. That's what we do, right? So a typical CNN architecture looks like this. There will be several convolution layers, pooling layers. There will be some batch normalization layers also. That is only to what happens during the convolution operation. It may happen that the data drifts away from, and there can be some drifting. So what we do that we typically normalize the data by putting it back to center and controlling the variation of the data, variance of the data. So for the whole batch, we normalize it, and therefore it is called batch normalization. So this can repeat several times, and then once it is done, the layers are this output of this convolution operation. This is flattened and is sent to a fully connected feed-forward network for classification. So this basically serves as a classifier, and this serves as a feature extractor mostly. This doesn't mean that these are not extracting features. These may also be feature extractor. So how does it flatten? So we just saw that we maps pooled, and we got 2 feature maps. So for each feature map, we will be one by one, we will be flattening them. That is what is known as flatten, right? So they use parameter sharing. Small pattern detectors called filters are used to convolve over the entire image. These filters are learned through neural network training in the same way as the fully connected network. Like the error is back propagated, gradient of the error is back propagated, and then weight adjustment are done, right? Weight adjustment, like each weight becomes is multiplied by the error. Say, let's take the partial derivative of this error function j with respect to delta. So the new weight value will be old weight value minus alpha times del j by del w. Okay, so just like hidden layers in a fully connected layer, convolution layers are used in CNN. To handle large size of image data, pooling layers are introduced. There are several CNN architectures that have come up, and these are some of the most frequently used networks. Recently used networks include for unsupervised learning, generative adversarial networks, and then we have come out with excellent attention-based convolutional neural networks. You have lightweight convolutional neural networks like GhostNet, MobileNet, and several neural networks have come up. There are CNNs with specific tasks like object detection, segmentation also. So let's take this specific application of object detection in images and videos. So this is an aerial image. The idea is to identify if there are aircrafts in the image, right? So you can see that not only that we are detecting that there are aircrafts, but we are locating them as well. This is very important from the point of view of various applications, like whether it is defense or it is fire detection from satellite images, or it is classification of different types of crops, or it is detection of diseases in crops from the satellite images. So it is very important that where is the location so that we can contain the disease and prevent the whole crop from the spread of the disease in the entire location. So especially these small objects are of great importance in object detection because they remain a challenge. When the object size is very small as compared to the image, the details, the texture, the various important characteristics or the features of the objects are not so well captured in the images. And therefore, small objects are always very challenging. Application. And what is segmentation? So my dear friends, classification is like you take this image and you classify that, okay, it contains cat class. It contains an object of class cat. The question is, where is exactly that cat? So that is known as classification plus localization. You localize the cat by identifying the location of the cat. So in case of single object, if this, suppose you have to look at from the images, you have to detect fire incidents. So detecting fire incidents requires only detecting one class of object. Single object, maybe it can be at one location, it can be at two locations. But let us assume that fire incident has just started and you're looking for fire incident through the satellite image. So you will be locating it exactly where it is, right? So that is a single object. So that is known as classification plus localization. But when we talk about object detection, there can be multi-class objects. For example, in a satellite image, there can be forest, there can be rivers, there can be settlement, urban settlement, there can be many other things. So these are different class of objects and their location. Right. So here in this cat class object, what is segmentation? Here, if we look at, we have three instances of objects and rest of it I'm not counting, right? So this is background. In the background, there can be trees, there can be many things, but we are not considering them as objects of importance for this particular problem. So I have got three instances. Two instances are of dog category and one instance is of cat category. And you can see that they are segmented. You actually find out the number of pixels that are belonging to the class of dog 1 and dog 2, right? These are different instances. So classification and localization, suppose you have labels. So flower, which is 1, I will be encoding it one class 1, I will be encoding in a vector of size 5, which is known as one hot encoding. Remember, this is known as one hot encoding, that each of it or 5 them as a 0 be having 0 1 2 3. That means first place, second place, rest of them are 0. So suppose there is a database, a data set which is having 5 categories of objects, right? And the corresponding labels. Okay. What will be CNN output? CNN output will be flower with a bounding box. Remember, it will be a classification plus a localization. So bounding box, how it will be outputting? It will give you the value of center, that is XY position of center, height and width. That will be that it will be doing. So basically your class, this is a classification and localization is a regression problem, because from here it will be giving two different types of output. One will be which class of object it is. Like for example, here it is flower class is probability 9.92. Rest of it is very low probability as compared to flower class, because you can see that the flower is very important. And then it will also give you where exactly is the flower. That is X, Y, W, and H. Right. So this is just a, for example, if the output is a 4096 size, so this 4096 to 4, like this will be giving me 4 outputs, and this will be giving me these 5 outputs. I hope this is clear to everybody. So localization is a regression problem. So object detection problem is a classification plus a regression problem. It's a combination of classification and regression problem. Accordingly, your CNN has to be designed. So the very first CNN model that was used was known as region proposal based CNN, region based CNN. It was a 2-stage method. 2-stage means in one stage we find out regions of interest, and in the second stage we find out in those regions of interest what categories of objects are present. So what happens that it proposes, this method proposes, the CNN proposes, the region proposal method proposes around 2000 regions, category independent regions of interest. So it's not looking at what category of object is this. It is only looking at what is the saliency of this region. So if it finds that, okay, this region is salient, it proposes this as a region of interest to the CNN, right? And then the classification is done using CNN after feature extraction of those regions. And then classification was performed using the standard, very popular method known as support vector machine. So here, CNN was used only for feature extraction. So let's take this example of an image, input image. So these regions of interest are extracted. They're all warped with the same size, into same size, right? And then they are sent to a CNN. CNN extracts features that it learns the representation of those images. And then suppose there are 5 categories of object in my data set. Then there will be 5 SVM. Remember, there will be 5 instances of SVM they will be using. And each SVM will be a binary classifier which will classify whether this region of interest is having object of class 1 or not. The second SVM will classify whether object of class 2 or not, and so on and so forth. So you can see that there are n number of SVM which are applied. So category independent region proposal defines the set of candidate regions for the detector, and the detector is what? Your CNN plus your classifier. So it's a large convolutional neural network, extracts a fixed length feature vector from each region. A set of class-specific linear SVMs are used for binary classification. So this is a selective search method that they apply for region proposals. So initially very tiny regions, you can see the corresponding region proposals. Then these regions are clubbed together. It is found that they are of similar nature, right? The size and the color and the texture, suppose, are the same. Then they are mapped, right? So they are clubbed. And similarly, so this further expands, and you can see that there are less proposals next time and less proposals. And finally, you have these 2 regions of interest. Okay. So you can see that because there were 2000 region proposals, so 2000 instances of conv neural network, and for each conv neural network, there will be there are 5 categories of objects. there will be 5 SVMs. Well, SVM is not that compute intensive, but these ConNets or convolutional neural networks are compute intensive. So to overcome this issue, faster RCNN or more efficient method was introduced, which is still considered to be one of the best methods, which is a two-stage method. So what do? They actually, did away with region proposal mechanism. They introduced the concept of a region proposal network. So region proposal network was trained, regions were proposed, and it went like to a single network, through a single ConNet, through a single network, we were able to identify all the regions of interest, and then that was sent to a classifier. Classifier can be again SVM, right? So that was these. So this is one method which is very important. It gives you high precision in determining, locating the object very precisely, right? But for real-time applications, like for applications involving drones, application involving IoT devices, or for say for autonomous vehicles, we need real-time methods. And two-stage method that I just discussed, that in one stage it identifies the region proposal, and in the second stage it categorizes those regions, classifies, categorizes, and detects what kind of objects are there. Instead of this, there was a method, this method was introduced by Redmond, a PhD student at that time, at the university, I'm getting the university name, but it's a very interesting method which is known as you only look once. What does that mean? It is a single stage method. In one go, the object, all the objects, all the categories, their locations are identified by the CNN. It was computationally fast, can be used in real-time environment. It is globally processing the entire image only once with a single CNN. And what is very interesting and important here is that it learns generalizable representation, right? So, if something is fast, it cannot be as precise. You know, if you are given the time to look for all possible objects, you know, you must have done this quiz, right, of identifying what is missing between, there are two images, what is missing in one image which is there in second image, right? Differences, right? If you are given sufficient time, you will be able to identify, say, all 10 differences. But if you are given only a small amount of time, you may not be able to identify all the 10 differences. That's what happened with YOLO. YOLO was very good in real-time detection, but it was not as high precision as faster RCNN, right? So YOLO has improved over the years. It was in 2015 that Redmond presented, and then CVPR is one of the top, it is actually the top conferences in computer vision, right? And its score is even more than the top ranked journal field, right? So I'm telling this for those who are new to this field. So CVPR how the image. needs only one forward propagation pass through the network to make prediction. It uses features from the entire image to predict each bounding box. And it also predicts all bounding boxes across all classes for an image simultaneously. And then it outputs recognized objects together with the bounding blocks. So while the YOLO design enables end-to-end training and real-time speed while maintaining high average precision. So let me, I would like to demonstrate, if possible, let me see. There's another single shot multi-box detector. So the object detection model. Here what we do, that here is an image. This is an image, you know. So this image is passed through the convolutional box to learn the features, learn the representation of the image, which we call as a latent representation. So what happens that with this image, the ground truth, that is where is the smoke, for example, in this case, it is here, somewhere here. The smoke is this. So this ground truth is also sent along with this. So it learns the representation, it understands the features, the characteristics of the smoke, for example. Suppose the the problem is to segment the smoke in the satellite image, right? Then this latent vector is passed through a decoder model, which is again a convolution blocks type, but these are known as deconvolution blocks. These are known as, they can be transposed convolution, which increase the size maybe of the convolution of the input. And then finally you get the area, the segment that is covering the smoke. That is what is known as a segmentation model. So generally the segmentation models are of this type. Encoder, they are of the type of encoder and decoder architecture, right? So you can see that each pixel they will be classifying as containing the object or not containing the object. So each pixel here, as you can see, has been identified. Like here you have smoke which is going like this, smoke which is going like this. So it is identifying that this all these pixels are smoke pixels, right? So these are the encoder decoder architecture. So and these are further examples of these. So in summary, I can say that machine learning is a branch of AI in which algorithms are developed that automatically learn the data patterns or learn the representation of the data to take decisions. And machine learning has led to developments in practically all fields that touch human life. The game changer has been deep learning. CNNs are promising architecture for vision-based models, but there is one very important challenge with the deep learning models. It works like a black box. There's no explanation of the predictions made by the deep learning model, when the model will fail, why it has failed. For example, in wildfire prediction or detection, there can be false alarm rates, high false alarm rates. If there is a false alarm, you know that it mobilizes the entire like wildfire protection from wildfire team. Lot of resources are mobilized. And so it is very important that false alarm rates be reduced. So if there is some detection by the deep learning model, we do not know what could probably have gone wrong, which has led to this decision. So interpretability of the model is not there. They work like black box. More recently, like from 2017 onwards, and especially 2019 onwards, in the area of vision, transformer networks have emerged. They are very powerful, lightweight models. They are efficient alternatives of CNN and RNN. And the new directions of research is on explainable AI, where we, given any prediction, the model not only predicts but also explains. You will see that just like if you ask a student or yes, you can hear me, right? So there are various. We keep running these important programs, like the next program. One program is already running on robotics. There's another program in Android programming, additive manifest. Think of any field, we are running these programs. So with this, I would like to thank you all for patiently listening.